Okay, let me start now. Well, I am Shujatra Bhattacharya, and I am second year PhD student from Indian Institute of Science, and I am doing research in atmospheric and oceanic science. So this course, this introduction to atmospheric and space science, is somewhat related, but space science, well, in I have done my BSc in physics, and after that I did my MSc Tech in geophysics. So in this geophysics, somewhat the space science are taught to us. So but now my research is on atmospheric and oceanic science. So it will be better that you also introduce yourself. Just 2-3 lines. No, a brief introduction will be enough. So one by one, if you can introduce, just wait a minute. Let me call out the name and just introduce. Wait. Yeah, Aditya Kumar Kisan. Can you just unmute and introduce yourself for two lines just? Hello? Yes, yes. Ah, Hmm. Great, great. Brilliant. Arun Kumar Nayak. Can you give a slight introduction in which background from you are? Yeah. Huh. Great, great. And what is your background? Physics or engineering background? Great, brilliant. Oh, great, great. Gadadhar Swain. Huh. Can you introduce yourself just slightly? Huh. Excellent, excellent. Gandhar Purandare. Huh. Excellent. Jyoti Pragnya Jena. Hello, am I audible? Fine, Geetika. Manas Ranjan. Yes. Ha, okay. Okay, fine. Science, which science? Physics. Oh, MSc Science. Okay, fine. Momita Haldar. Yeah, excellent. Okay, great. Pradeep Kumar Shahu. Good evening. Okay, excellent. Pratima Rani. Hello. Excellent. Great. Prayas. Good evening. Excellent. Fine. Rahul Singh. Okay. Okay. Hmm. Excellent. Excellent. Very good. And Ranjan Kumar Jana. Hello. Ah, yes. Okay. Renu Raghavi. Rosalind Pradhan. Yeah. Excellent. Sahil Biswal. Hi. Good evening. Yeah, great. Sambit Kumar Barik. Good evening. Excellent. Shantanu Patel. Okay. Shubhadvani Sardar. Yes. Excellent. Shubha Lakshmi Mishra. Hello. Good evening. Hmm. Okay. Shubham Nayak. Excellent. Taranya Nitish. Ah, yeah. Okay, fine. Thank you. Now I will share my screen. As I've introduced you, I'm Shujatra Bhattacharya, second year PhD student at Indian Institute of Science, and I am currently pursuing my research on atmospheric and oceanic science. So this course is somewhat related to me, and my background is earlier I have done MSc Tech in geophysics with specialization meteorology, which is related to atmospheric and you can say oceanic science somewhat. Space is somewhat related to that. And before that, I did my BSc honors in physics from University of Delhi. Okay, so now in this course, as you have seen that it is mostly towards this the atmospheric phenomena which you see everywhere, like cyclone. You hear about, you listen to several news about cyclones and different weather phenomena. For example, those people who are in the northern India, they generally see some western disturbances. Suddenly in the winter, some cloudy conditions and rainfall. So these phenomena, and along with that monsoons, which is a big phenomena because about for which our agriculture is terribly affected when monsoon is bad or poor. So these phenomena we will study using certain forces, some dynamics and thermodynamics, using some thermodynamical concepts and dynamical concepts, which are very basic concepts which you have studied in your BTech, maybe BSc, MSc physics, and also class 11, 12th also science. So these concepts will be used here and to study those particular phenomena, to understand the physics behind those phenomena. So without wasting my time now, I will share the screen. Just a minute. Can you see my screen? Okay. Can you see the presentation, by the way? Can you now see the presentation? Hello? Hello? Okay. Huh? My voice is cracking, is it? Okay. Wait. Now it is clear, is it? Okay, fine. I will start now. Uh, so as you know, this is the course Introduction to Atmospheric, not Oceanic Science, but Space Science. And this is the week 1. So I will start with, let me just turn off my video here. Okay. Now, okay, fine. Now, so you can see that first thing which I will cover here, that is sun, a basic structure which I have given here. The structure of the sun from the core to the top of the atmosphere. It's a little bit revision kind of thing. The theoretical details, of course, you can see the week lectures and videos which are uploaded in the NPTEL. So I will just give a very brief introduction about the sun. So some people are still joining here. Okay, let me start. So first is the core. So this core is having a temperature of some 15 million Kelvin. So why this is happening? Because of some fusion reaction, nuclear fusion reaction. Hydrogen is fusing to form helium and some energy is released. So nuclear fusion reaction is resulting into this terrible amount of energy over this core region, and as a result of which you are seeing that 15 million Kelvin is the temperature, which is too high. As you can understand that Earth's global temperature is about 288 Kelvin. So about 15 degrees Celsius. So as compared to 288 Kelvin, of course, 15 million Kelvin is very, very large. And this is particularly because of this nuclear fusion reaction. Now, of course, any body which is having some temperature T, it will radiate. Except for 0 Kelvin, any body which is having some temperature, it will radiate out. So core which is having too high temperature, definitely it will radiate out certain energy. So this zone just after the core, suppose this is the core, I am doing a cross section kind of thing, this is suppose the core, and after that some radiation zones are there. So here it will radiate into the space, not space, just into the next layer it will start radiating. After that, because of the temperature gradient, suppose here up to which it starts only radiating, and you can see that this is the photosphere of the sun, or the surface of the sun. This is the surface of the sun, which is called the photosphere, and you can see that its temperature is about 5800 Kelvin. So this 5800 Kelvin, and of course this temperature will be much high. So this T1 temperature which is here, and this is T2 which is 5800 Kelvin. Because of this gradient in the temperature, convection takes place. So that's why this region is named as convective zone. So here the convection cells generates. So high temperature, because of low density, it tends to go upward, and after that it tends to that cooler regions as compared to this T1 region will tend to go down. So these convection cells are appeared in this sun's surface as some bright and dark patches. So more bright means high temperature, from the high temperature the cells are coming, and means it is coming from the higher temperature region from here, and when it is somewhat darker, that means the lower temperature region which is going down. So this is how this convection zone and photosphere region is. Now in this photosphere there are further some dark flecks. Of course there are some brighter and less brighter regions in the over the surface of the sun, but there is still very darker, much more darker than these convection patches. Much more darker spots are present, which are known as the sunspots. These sunspots generally occurs in pair, and it is associated with the magnetic field, some complex magnetic field inside the sun. Just above the photosphere is the chromosphere, which you have already studied in this course already. So this is the lower layer of the atmosphere, which have some emission of hydrogen or solar prominence, and above which the temperature suddenly rises, which is corona. Now why the temperature of the corona is about 1 million Kelvin is still not very clear. Maybe due to the ionization which is process occurs by some spectroscopy measurements people have seen, scientists have seen that this corona region is having more ionization, because of which some energy is released, and that's why the temperature is too high. But the question is that when we see from the earth or from any other places, what we see is the photosphere, the emission from the photosphere. We always talk that 5800 is the temperature of the sun, and from which the emission takes place, and we are getting that bright light. So why not corona, which is having a much higher temperature than 5800 Kelvin? This is because of very low density of corona. So particles or the gas ions are so less there that, or gas particles are so less that you will, per unit volume, per unit centimeter cube, suppose, it is so less that as compared to the photosphere, that its temperature may go up, but it is not contributing to too much high emission. So only during the solar eclipse region, solar eclipse time, we see suppose when this is the sun, suppose, and moon has blocked already. So these regions we see as these corona regions can be seen at that time. Otherwise it is not seen. So this is a very brief introduction of the sun. The detailed introductions are discussed in the lecture notes and whatever is provided to you, definitely. And we will see from here that how can we say that this temperature of the photosphere is about 5800 Kelvin using some basic laws of radiation which we have all studied. So let's see. So basic laws of radiation. What are the basic laws of radiation which I will discuss here? There are many laws, as you know, that Planck's law is there, then Wien's displacement law which I will be talking about, then there is another law which I will again state, that is the Stefan-Boltzmann law. So these all laws are very important laws of radiation, and from which we can deduce that what will be the temperature of the photosphere of the sun. Maybe say you can say that in which wavelength range will a body at a particular temperature will emit radiation. So these things we will look one by one. Fine. So first is that Wien's displacement law. As you already know that Wien's displacement law is stating that lambda max. What is this lambda max? It is, so let me go here. It is this thing. This is the spectral energy density plotted with wavelength, and this is the Planck's law graph. There is a Planck's law that gives this particular pattern of graph. Now for each temperature you can plot these graphs. Say for 3500 in the bottom, then 4000, then 4500, 5000 and 5500. And you know that corresponding to the highest density, energy density of a particular temperature, let's say 3500, its maximum intensity lies here, peak is here, and its corresponding wavelength is here. Let's say, for example, for 4000 Kelvin, its peak lies here and it is going here. For 4500 Kelvin, it is going here. So you can see that lambda max represents that it is the wavelength corresponding to maximum energy density. It's corresponding to maximum energy density is the lambda max. It is not the maximum wavelength. It is the wavelength corresponding to the maximum intensity. Fine. Okay. So lambda max will be inversely proportional to the temperature of the body. So lambda max is equal to B by T, where B is found out to be this particular constant 2898. Remember the units here. I have written it 2898 Kelvin micrometer. So the wavelength will be, if you calculate with any temperature in Kelvin, then the wavelength will be coming in the micrometer. Remember this 2898 is for micrometer. Okay. Now see, this is the solar spectrum of the sun. Now you can see that the peak is almost near 500 nanometer. So what is this 500 nanometer? 500 nanometer means what? 500 into 10 to the power 9 minus 9. Nanometer is minus 9, 10 to the power minus 9 meters. I will convert it into micrometer. So how much it will be? 0.5 micrometer. Just divided by 1000. So 0.5 micrometer is the lambda max. That is wavelength corresponding to the maximum energy density of the solar spectrum. Now, if I have this lambda max, then using Wien's displacement law, can I write then what will be the temperature? So T will be what? B by lambda max, because if you see the earlier thing, it is lambda max is equal to B by T, just changing the direction. So temperature will be equal to B, which is, I have already stated, it is 2898 micrometer Kelvin divided by lambda max, which is 0.5 micrometer. So this is the thing. So let me calculate it and write the result here. How much it comes? 2898 divided by 0.5. It comes out to be 5796. You can check the calculation also. 5796 Kelvin. And what we have seen, the temperature of the photosphere, it is about 5800 Kelvin. So nearly same, 5800 Kelvin. So using this Wien's displacement law, simple basic law of radiation, see, we can find out, if we know the solar spectrum definitely, we can find out that corresponding to this maximum wavelength, what will be the temperature of the photosphere of the sun. This is one of the exercise which I have shown you. Okay. The next thing is that another basic laws of radiation, that is the Stephens-Boltzmann law. What does it say? Energy per unit area per unit time. This is represented by E. It is not energy, it is energy per unit area per unit time. Energy per unit area per unit time emitted from a body is directly proportional to the fourth power of temperature. And the proportionality constant is sigma, which is the Stephen-Boltzmann constant, which is given by 5.67 into 10 to the power minus 8 watts per meter square per Kelvin to the power 4. You can check the units. And this epsilon is the emissivity. Epsilon I have written here, emissivity of the body. That is how much a body is emitting as compared to a perfectly black body. Now here in this case, we will assume that sun is a perfectly black body. Also earth is also a perfectly black body. For time being, we can consider this. Earth as an approximation, it's not a perfectly black body, but we will consider it as a perfectly black body. Okay, so if it's a perfectly black body, then emissivity in both cases is 1. Then E will be equal to sigma T to the power 4. That's all. Now, what we are going to do with this? What we are going to do with this is that, so this is the EM spectrum I have drawn to show you that suppose you have earth, right? You have earth, and I have told you that the global average temperature of the earth is 15 degrees Celsius to 88 Kelvin. Of course, due to the global warming, some increase in temperature is seen, but right now I will focus on whatever is the theoretical number, which is, or the measured number, it is 288 Kelvin. Now again I will apply that same lambda max thing, the Wien's displacement law. The emission thing I will come later, this Stephen-Boltzmann law. This is another exercise for that Wien's displacement law only. So lambda max is equal to 2898 divided by 288 Kelvin. So if you do it, it comes out to be about 10.06 micrometer. And see where 10.06 micrometer, roughly 10 micrometer lies. So this is 10 to the power minus 6. that is 1 micrometer. So 10 into 10 to the power minus 6 is 10 to the power minus 5. Somewhere here it lies. That is, Earth generally radiates in the infrared region. Earth generally radiates in the infrared region. Now, for sun we know that the lambda max is about 0.5 micrometer. We have seen the solar spectrum, so I am not doing it again. So 0.5 micrometer. Where this 0.5 micrometer will lie? It is in the visible, this region. That's why most of the radiation from the sun which we are receiving is in visible region of the solar, this EM spectrum, from 400 to 700 micrometer. Okay, so this is what I was trying to say to you. First is this EM spectrum is more common to you people, so I am not discussing it further. Okay. Next thing is that how much energy is emitted by the sun. Okay, so it is corresponding to emission, so I will use that Stephen-Boltzmann law. So what does this Stephen-Boltzmann law says? Stephen-Boltzmann law says that energy per unit area per unit time is equal to sigma into T to the power 4. I have assumed emissivity is equal to 1. Fine. So T, what is the T of the sun, the photosphere? 5800 Kelvin. So this will be 5.67 into 10 to the power minus 8 into 5800 Kelvin to the power 4. And if you calculate it, let me calculate it again and find out what is the result. Well, it comes out to be about 164 532.32. You can neglect this part also, it's fine. So this is the amount watts per meter square which is emitted from the sun. Because why watts per meter square? Because energy per unit time is watts and per meter square is the per unit area. So this is the amount of energy which is emitted by the sun. Now this is the energy per unit area per unit time. Now what is the energy per unit time emitted by the sun? We have to multiply with the area of the sun, right? Surface area of the sun. The energy per unit time emitted by the sun. We are heading towards something actually. That's why I am proceeding in this way. So this is the sun which is emitting in all direction, right? It is emitting in all direction, and let us say its radius is Rs, and this radius value is also fixed value. So Rs is about 696340000 meter. So this is up to kilometer. So this is the amount of kilometer. In kilometer it is about 696,340 kilometers. So it's too large a distance. Fine. So this is the Rs. So what will be the area therefore? The area of the sun, the surface area of the sun is 4 pi Rs square. So what it will be? 4 into 3.1416 into 696,340,000 square. And ultimately, if you multiply this with energy, to E into A, if you do, what you will get? So suppose this is E, energy per unit, area per unit time. The energy into area, that is the energy per unit time, let it call it small e, that will be equal to this number times this, and if I calculate it, it will be roughly coming out to be 3.9 into 10 to the power 26 watts. So you can imagine that this is the amount of energy per unit time is lost by the sun in all direction. Fine, this is the total energy emitted per unit time, so that's why its unit is watts. About 10 to the power 26 watts it is emitting. Well, so what? Why we are calculating all those things? Because there is an important factor in Earth which is known as the solar constant. I will come to it, this solar constant, what is the definition of the solar constant. Before that, another thing needs to be done, and that is this distance of the planets from the sun. This is an empirical relation given by Bode's. So it is called as Bode's law. Bode's law, these are the empirical relation where n represents the number of planets, means the nth planet, I would say, not number of planets, but the nth planet. So starting from Mercury, Venus, Earth, Mars, and like that way, proceed. So this is the observed distance in the y-axis, and this is the distance from the sun predicted by Bode's law, and it comes out in a very good shape, except for Pluto, which we can neglect for a time being. We are only focused on the Earth. Okay, so the distance from the sun and Earth is about, the graph says it is about 1 astronomical unit. So you can check it with this formula also. So which planet is Earth? How much will be the value of the n? It is the third planet, right? So n is equal to 3. Mercury, Venus, Earth. So n is equal to 3. So d of 3, when n is greater than equal to 2, we will use this formula. So d3 is equal to 0.4 plus 0.3 into 2 to the power 3 minus 2. So it is 0.4 plus 0.3 into 2. So it comes out to be 0.4 plus 0.6, that comes out to be 1. And these all dn's are in astronomical unit. Now what does this 1 astronomical unit in meters? That is about 1.5 into 10 to the power 11 meters, or 1.5 into 10 to the power 8 kilometers. This is the astronomical unit. So remember this thing. This 1 astronomical unit is the distance between the planet and that is the Earth and the sun is fixed. That is 1 astronomical unit. Well, now what we have seen? We have already seen that the energy emitted per unit time. Okay. Someone has said, sir, please repeat the Bode's law again. Bode's law is nothing but an empirical relationship to fix it, to find out what will be the distance between that planet and the sun, where n is the nth planet. So if we start with Mercury, that will be n is equal to 1. For others, it will be 2, 3, 4, like Venus, Earth, Mars. Some asteroid belt comes, then Jupiter, and like that way. Okay. So this is the relation. Dn is equal to 0.4 plus 0.3 into 2 to the power n minus 2 for n greater than equal to 2. Means from Venus, this will be the equation. This is an empirical law. So this is not a very physical concept based law, just to fit this particular curve, which is the observed distance. Okay, using this I have just calculated 1 astronomical unit, or else people know that observed distance from the sun and the Earth is 1 astronomical unit. So 1 astronomical unit is about 1.5 into 10 to the power 11 meters. Now why we are doing it, we will see in the next slide. So now a very important concept is the solar constant. So what is a solar constant? Solar constant is the amount of energy of the sun received per unit area of the top of the atmosphere. So you have the sun here, and you have the Earth here, and at the top of the atmosphere, how much energy of the sun per unit area is received. That is to be calculated. That is the solar constant. It is widely used in the radiation physics in our course in the atmospheric physics. So this constant is very important. So that's why, in fact, I have seen the videos in the NPTEL also. They have mentioned about this solar constant, about 1370 watts per meter square. But I will also calculate it will be more near to this particular value. Not exactly maybe this value, because several approximations and things that I will use. So what is happening is that we will roughly take that this atmosphere, in the top of the atmosphere to the sun's surface, that region, the distance is about 1 astronomical unit. Although you know that it is from the surface to surface. Fine. So this is the roughly the 1 astronomical unit distance, and we also know that the energy emitted per unit time by the sun. Okay. So what I will do is that, so this energy is emitted from the sun in all direction. So I have to divide it with this 4 pi r square. This r is this particular one astronomical unit, the distance, because this energy is emitted in all direction. So I have to make a circle such that we can find out the energy per unit area received at the top of the surface of the earth. Fine. This is the concept, that how much energy emitted by the sun per unit area received at the top of the atmosphere. That's all. So the solar constant denoted by S will be equal to the energy emitted per unit time by the sun in all direction divided by per unit surface area. So surface area is this 4 pi, because the distance we are talking about the earth's receiving. So it is 4 pi into r square. And what it will be? So 3.9 into 10 to the power 26 watts we have calculated already, divided by 4 into 3.1416 into that one astronomical unit I have already defined, that 1.5 into 10 to the power 11 square. And I have calculated, and it comes out to be nearly about 1379 watts per meter square. Although its absolute value is about 1370 watts per meter square, some assumptions like this may result into some fluctuations in this value. But we can see that it is nearly coming towards this 1370 watts per meter square. So this is how the solar constant is defined. It will be used particularly for radiation balance, that how much energy is reflected back from the surface of the earth. In that case you will use this solar constant. But what is solar constant? It is at the top of the atmosphere. Then what will be the solar constant, or what will be the what we call as the insolation at the surface, we will see now. So see, I have written here insolation average is about, means average insolation over the earth surface is about solar constant divided by 4, because solar constant is at the top of the atmosphere. Now we will see that how it is being done. So you can see that solar constant is already defined as the energy per unit area received at the top of the atmosphere. What we have done is that, what people have done is that they have taken a disk. They have taken this disk, and this disk is of radius equal to the radius of the earth. Radius equal to radius of the earth. Or of course that earth is not a complete spheroid, it's an oblate ellipsoid. So polar distance, polar radius and equatorial radius will vary. But here we have assumed that it is same. RE will be equal to same 6370 kilometers. Okay. So this is the thing. But it will not matter much, because if you see how we are proceeding here, so this insolation is solar constant by 4. How we are coming into this particular thing, I will show you. So solar constant is the energy which is received at the top of the atmosphere. Now we will see that how much energy is received at this particular disk. We are covering this whatever occurring inside the sun, radius, temperature, nuclear fusion is just a prediction, or it's already experimentally verified. Some research is going on. I am also not very sure that how they are talking about this particular thing. Of course they have some valid point, some research they have done. They are not predicting, maybe some experimental, some model kind of thing they have developed, through which they have tried to say that this is the particular nuclear fusion reaction, and because of which the temperature is like that. Fine, coming back to this insolation concept, that this surface of the disk, we are considering this as a surface of the earth. Okay, now this disk I am using, not the entire surface, which is the spheroid kind of surface, but we are assuming that all the energy which is received by the earth is in this particular disk, which is the maximum longitudinal circle, or the maximum prime meridian, what you call that circle. If you complete that in that disk, how much energy it is receiving. So solar constant is, suppose S is the solar constant which is received. Now how much energy it is received at the disk is S into this pi into RE square, right? Because why? Because this is also energy per unit area per unit time. So I am multiplying with the area in which the energy is received. So this will be the total energy received at the surface, because I have assumed that all the surface is now compacted into this particular disk. And now this is the total amount of energy per unit time received by the surface. Now over the entire surface, what it will be? This will be divided by 4 pi r square. So this pi r square, pi r square will go out, so it will be S by 4. Fine, so this insolation, average insolation is I is equal to S by 4. So the insolation, the amount of energy which is received at the surface of the earth is solar constant divided by 4. This is a very, very brief kind of thing to understand what is the insolation using the solar constant. We can calculate immediately. Fine. Next, we will go to the insolation summer and winter. Let me leave this slide right now. And this is a kind of a figure. So this is the annual average insolation you can see. And if you roughly average this annual average insolation, it will come out to be about S by 4. So S, what is S? S is about 1370 as defined. So if you do S by 4, it comes out to be, let's see, 1370 divided by 4 is 342.5. So surface is averagely receiving, that surface of the earth is receiving an average radiation or average energy of 342.5 watts per meter square. Okay, so if you now annual average graph, if you latitudinal weight and average it, the global average will come, and that comes out to be 342.5 watts per meter square. You will see that. But during different times it becomes different. For example, winter solstice, summer solstice, this thing I am discussing right now. So what happens is that we know that sun is at the Tropic of Cancer during the summer solstice. Summer solstice means say June 23. June 23, roughly it varies sometimes from 21 to 24, it is fine. June 23 is the summer solstice. Okay, then these are defined on the basis of the northern hemispheric summer and northern hemispheric winter. And then winter solstice is in December 23 nearly. And there are some equinoxes which are known as the vernal equinox and autumnal equinox. Sorry, okay. Just autumnal equinox, and this is vernal equinox. Fine. This happens in 21st March, which is coming in the next month, and this will happen in September, as you can see the name, autumn. So it is 23rd September. Okay, so these dates don't go by these dates, it ranges between 20 to 24 or 25 of those particular months. Now what exactly happens in this thing? Well, you see, this is the sun. Okay, now Earth's position I will draw. Suppose here this is the first position, this is the second position, this is the third position, and this is the fourth position. Earth is revolving. Okay, Earth is revolving around the sun, and these are the 4 positions I have seen. And we already know that Earth also has a tilt. There is a tilt of the Earth. About 23.5 degrees is the tilt of the Earth. And remember one thing, that seasons, any season which is occurred, seasons generally occur because of the tilt, not because of the distance. Why distance I am saying? Because sun is in one of the focus. If you remember the Kepler's law of planetary motion, then the first law says that sun is in one of the focus, and other things in a particular orbit, the planet revolves around that. So one is the apohelion, another is the perihelion. So the perihelion is the nearmost point and the apohelion is the further point. So because of that, this season does not occur, because ultimately if you see the distance, these distances are not much to impact these seasons, but this axial tilt generally impacts this season. So I will discuss a little bit after this. So what is happening is that this is sun. So you see this particular region. Let me change the color. You understand it well. See, this is now my equator. This is the equator, just perpendicular to that the axis of rotation. This is the equator, this is the equator. So you can see that these 2 points, not much change in the sun's radiation will occur in the different hemisphere. That is, northern hemisphere and southern hemisphere will get same amount of radiation, almost equal amount of radiation. Similarly here also it will get similar amount of radiation. But what about this one? In this one you can see that this is nearest as compared to this. So the solar radiation has to travel a longer path in the southern hemisphere as compared to the northern hemisphere. So that's why we call this as a northern hemisphere summer. Whereas here you can see that the southern hemisphere is more close to the sun's rays as compared to the northern hemisphere. So we call this as the southern hemisphere summer or northern hemisphere winter. So these are the regions of this summer solstice, and this is the region of winter solstice. Southern hemisphere summer means northern hemisphere winter, so that's why it is winter solstice. And the other 2 positions are the equinox position. So from summer to winter if you go, so this will be the autumnal, because from summer to winter if you go, the autumn comes in between. Whereas from the winter to summer if you go, this is the vernal, the March season comes. So this is the vernal equinox. So this is a picture of the seasons. One must know, when people are studying about the atmospheric and space sciences, people must know these particular diagrams. Another important diagram I want to show, that people must you people must have heard that during our summer season, northern hemisphere summer season, you must have heard that the polar regions, the Arctic region, or that Greenland or this Arctic polar regions, they generally get 24 hours of sun. So they call the term midnight sun. So why this happens? This happens because, suppose this is your earth. Now I will draw the earth somewhat larger, and this is the sun. Okay, so sun is giving radiation in all direction, fine, it's absolutely fine in this. Now there is an axial tilt in the earth that we know, and this is the equator, no doubt about that, perpendicular to this. And suppose this is the polar region, okay, say some 60 degrees north to 90 degrees north. What are these 60 degrees, 90 degrees north? These are latitudes. And this is the the southern pole. Again, this is 60 degrees north, 60 degrees south to 90 south. Fine. Now I will change the color. Now this is the day region and this is the night region. So see, this is the thing comes. Okay, so if you see the tilt, as I have shown in this case, northern hemisphere summer, kind of this thing happen. So more the radiation are not traveling much as compared to this. Radiation is traveling much more in the southern hemisphere as compared to northern hemisphere, because it is tilted towards the more towards the north. Fine. So this is the night time. So if you see, southern hemisphere polar region is completely covered, so it is 24 hours night. It is not receiving any insolation or any radiation, so 24 hours night. And this region, see, this region is receiving 24 hours daylight, so it is 24 hours day. Very interesting concept, very interesting way everything is designed. So this is another thing which I tried to discuss with you. This is very interesting thing, that 24 hours sunlight, which we call as a midnight sun. So this is the reason for this particular thing. Okay, somewhat I think this idea will be clear. Now moving on to the next slide. This I have already discussed. Now, okay, in the assignment 1, I have seen that there is a question related to escape velocity. Not much numericals are there, mostly based on some concepts, theoretical concepts. If you read those slides, you will easily get those concepts. Only one numerical I have saw, but I will not give the numerical solution right now, but I will give you what is the concept of the escape velocity, although people know it. What is the concept of the escape velocity? But let's do some physics here. let's again, those who knows this properly, then it will be a revision for them. So what is escape velocity? Excuse me. So this escape velocity is any planet or any star, suppose any planet or any star you have, and you have a mass, and it wants to go from the gravitational field of that particular planet. So suppose this is the gravitational field of a particular planet, although this in this way it should not be drawn. So suppose this is the gravitational field of a particular planet, it wants to escape this particular gravitational field and go free. It is in the binding now with the planet because of the gravitational attraction. Now it wants to become free. So for that, how much amount of velocity this particle should have so that it can cross? In terms of energetics, how we can say? In terms of energetics, we can say that, see, this is V. V means some motion is happening, and motion related energy is kinetic energy. So simple. So kinetic energy of that particular body, kinetic energy of the body should be equal to the work done against gravity, because since suppose we are throwing a ball. So when we are throwing a ball, this ball, when it's going in the upward direction, it is working against the gravity because gravity is in the opposite direction. So it should be equal to the work done against gravity. I have to introduce the concept of work done because we are dealing with the energy right now. So work done against the gravity. Let's calculate what is the work done against the gravity. How we can calculate the work done against gravity? It's simple. Let's draw it again. This is the Earth. This is the radius of the Earth, and suppose from here it is going up. Fine. We don't know up to which region this gravitation field exists, so let us take up to infinity. And there is a mass which is present here which wants to escape. Gravity is in this direction, that is the acceleration due to gravity is in the opposite direction, or the gravitational force, I would say the gravitational force is in the opposite direction. This is of mass m, the Earth is of mass capital M. Let us consider, because we know that Newton's law of gravitation requires the two masses. It's an inverse square law. And let us define a distance x, and let us define a distance dx. Okay, dx is the element, distance element I have taken as dx, and x is this direction, which is opposite to the direction of the gravity, acceleration due to gravity. Fine. So what is the definition of work done? Work done is what? Work done is force into displacement. So force is what? The gravitational force, gmm by x square now, because I have taken a variable x which is varying. Fine, gmm by x square, and the element dx which I have taken is opposite to the direction of the force, because force of gravity is acting downward. It is pulling this mass towards this, is trying to pull this mass towards the center. So gmm x square into minus dx I have to put. Okay, and how, from where to where I will integrate? I will integrate from the surface. I am starting from the surface and to infinity, because from the surface of the Earth a mass is present. From there to infinity I have just doing it. So this will be the work done against gravity. So what it will be, therefore it will be a minus sign will be there outside, and so it will be gmm and dx by x square. So dx by x square r to infinity, so it will be again minus gmm 1 by x with a minus sign, and from r to infinity, and so what it will come as minus gmm 0 into minus plus, so 1 by r. So this will come. Negative work done means what? It is doing work against gravity. Nothing else is this negative sign meaning. It is just against gravity. So when we will equate this with the kinetic energy of the body, we don't need this minus sign, because minus sign is representing us that this work is done against the gravity, the way we have defined. Okay, so work done against gravity we have calculated, it is minus gmm by r. Well, so kinetic energy is what then? Half mv square. It has still not got into that domain of special theory of relativity, so it is half mv square right now, and that will be equal to the gmm by r. I am not taking the minus sign because it is just a representation that the work done against the gravity is that negative sign. That's all. So now when I am equating this half mv square with gmm by r, the work done, this v should be equal to ve. That is the escape velocity. Nothing else. Just the notation. Okay. So what we'll do, this mm we can chop out easily. So ve square will be equal to 2 gm by r, and ve will be equal to root 2 gm by r. This is the escape velocity. Well, in terms of some known variables, we know that the acceleration due to gravity g is equal to gm by r square, where r is the radius of that particular planet or star, m is the mass of that particular planet or star, and g is the acceleration due to gravity for that planet or star. So what we can do is that ve is root 2 gm by r. Fine, I multiply with r, I divide with r. So what I will get? I will get root 2 gm by r square into r. So what I will get again? 2 gr. This is the escape velocity of a body which depends on the acceleration due to gravity of that particular planet or star, and r, the radius of that planet or star. That's all. This is the escape velocity. You can calculate the escape velocity of the earth if you want to. Well, we can calculate g, we know it's 9.81 meters per second square, and we know the radius of the earth is about 6370 kilometers, so 000 meters. Put that value, v is equal to root 2 into 9.81 into 6370000, and ultimately you will get about 11.2 kilometers per second. So this is the concept of escape velocity. Physical concept of escape velocity is this. Now you can apply this concept to do that assignment 1 question. We will discuss in the next week's lecture all those assignment solutions, because tomorrow is the last date of the assignment submission, so I cannot right now discuss the solutions. Okay, a very important thing as an atmospheric and space science you are studying, so this is a very important thing we must understand, that is the Milankovitch cycle. And I think in this course it will come somewhere, this Milankovitch cycle, or I have heard maybe in the second lecture or somewhere. So this Milankovitch cycle is interesting to share with you. I will like to share it with you. This is a very good concept, very interesting concept as well. So what happens is that 3 oscillations takes place. 3 oscillations takes place. One is of the eccentricity of what? Eccentricity of the orbit. Eccentricity of the orbit between Sun and Earth, or Sun and any planet. Second is the obliquity. What is this obliquity? That the tilt, the axial tilt which is there. And the third is the precession, that is this tilt is also changing. So these are 3 things I will discuss in details. So I will discuss in details these 3 things which are quite interesting to see. So what you know, that this eccentricity is seen to vary. Actually, how these things are known, because you see that these are written in thousands of years. So thousands of years oscillations, how we have measured? We have measured using some paleoclimatic evidences. Paleoclimatic evidences means some what you call as below the ocean, some carbonate shells, corals, and with the help of some we say it's some dendrochronology with the paleoclimatic evidence of the tree samples. Based on that also we can predict the rainfall also even with that. So those monsoons at that time, some kilo years ago, what is the monsoons? These also we can do using this. So this is the paleoclimatic data. Using this paleoclimatic data, we can come into these kind of conclusions. So what happens is that it has been seen that this Sun-Earth orbit which is there, it changes from, see, this is the elliptic condition to the absolute circular condition. So elliptic to circular to again come to elliptic requires 100 kilo years. So this is an oscillation. 100 kilo years is its time period. So from elliptical orbit to circular orbit, again coming back to the elliptical orbit. This is what is your role as eccentricity. Why we are calling it as eccentricity? Because eccentricity, if you know, remember, of the ellipse is, I think, 1 minus b square by a square, where b is the minor axis, semi-minor axis, and a is the semi-major axis. So in case of circle, it will be, b will be equal to a, because that is equal to the radius. So ultimately this will be 1 minus 1. These are same. So E will vary from 0 to 1. So E will vary from 0 to some value, not 1 maybe, some value, and again come back to 0 in 100 kilo years. 100 kilo years means 100,000 years. Again, for second thing is, second oscillation is the obliquity. What is this obliquity? This axial tilt. This axial tilt, right now I have told you that the axial tilt means what? Over that axis, Earth rotates. So what is this tilt means? Tilt means that, suppose this is my Earth and this is my orbit. This is the orbit in which this Earth revolves around the Sun, and this is the tilt, which I am saying that it is 23.5 degrees tilt. So 23.5 is the angle between this. This is the 23.5. Fine. This is the 23.5 degrees tilt. So this 23.5 degrees tilt also changes. It also varies from, say, 21 degrees to 24 degrees. Again come back to 21 degrees in, say, 41 kilo years. You see this oscillation, it is nearly about 40. Roughly, if you start from here, it will come here. So 41 kilo years is the time period of oscillation of this particular thing. So this changes. And the third thing is the precision. Precision of what? This axial tilt only. These 23.5 degrees today is here. Now it can be possible that after, before some time or after some time, it may change up to minus 23.5. So this is called the precision. So in general, it is seen that this precision has occurred earlier, and because of this precision, what happens is that this precision period is about 22 kilo years. So now what happens is that if this precision period is about 22 kilo years, and today it is about 23.5 degrees, and earlier it was minus 23.5 degrees, then what will change? You know, the seasons will change. 11,000 years ago, at that position, the diagram which I have shown earlier, see this one, yes, this one. So here I have told that this is now 23.5 degrees tilt. Now what happens is that 11,000 years ago, this tilt would have been this. Now what is happening? These things is not changing. These things are not changing, but these two things are changing. What is changing? Now today, where there is a northern hemisphere summer, now 11,000 years ago it is a southern hemispheric summer, whereas 11,000 years ago this is this position, today it is southern hemisphere summer, that day it was northern hemisphere summer. So this is how the seasons will change because of these particular oscillations. That's why it is very important and interesting as well in this particular subject. Okay, so these are the three oscillations which is seen. Okay. This is known to you, Kepler's law of planetary rotation. First law, as I have already mentioned earlier, but why we are studying, you will see in a little while. We are actually trying to calculate the mass of the sun. So we will study about what will be we will calculate out what will be the mass of the sun, and which we know that it is 10 to the power 30 kgs, nearly 10 to the power 30 kgs. So we will see with these laws, particularly the third law, that what will be the mass of the sun. We will calculate that. So first law is very easy to understand, that sun is one of the focus and another the planets rotates in the orbit. Second law is conservation of Yes, someone has raised hand, I think. Anyone has any questions? Okay, fine, I will continue. So this Kepler's law, second law, is based on the angular momentum conservation. As you can see, this it generally tells that a planet sweeps out equal areas in equal intervals of time. So if you see this particular thing, and this is suppose d theta, and this is definitely rd theta, because if this is r, so it will be rd theta. This arc is rd theta. So rd theta into r is the actual area swept. So r square d theta. Now the second law tells that da by dt is constant. It is 0. So now this r square d theta by dt, if you do, because d dt of a dA, so r square d theta dt, this is nothing but the dl dt, that is equal to 0, because L is nothing but r square theta dot. So I think this, this should be constant, I think. Equal areas in equal intervals of time, so this will be 0, and this r square theta dot is constant. Angular momentum conservation. Fine. The third law is that time period of revolution, square of the time period of revolution is proportional to the semi-major axis cube, But in case of for simplicity, we will take it as a circular kind of thing and take the radius as the that particular radius of this particular region, planet. Okay, so in this Kepler's law, this is the only thing which I have discussed. I will not discuss much. And for the mass of the sun, I will discuss in a little while. Okay. So suppose so what happens is that, suppose this is your sun and this is your earth. This is the distance, and this is revolving. Definitely this is revolving around the sun, and this distance is known to us very well. This is r is roughly equal to 1.5 into 10 to the power 11 meters, the one astronomical unit. Okay, so this is my mass ms, and this is some small m maybe. Okay, so the concept is here, the gravitational interaction between these two is balanced out by the centripetal force. So what we will say is GMS m by r square will be equal to m v square by r. Now this v is equal to omega r, so I can write this as v is equal to omega r, the angular velocity, right? This is the angular velocity, so v is equal to omega r, the angular velocity, that is equal to 2 pi by t, the time period of revolution, therefore, into r. And so it's v square, so actually it should be m r omega square, because r will be cancelled out. So you will have g ms m by r square. You can chop, so it will be g ms will be equal to r cube into omega square. We have already, sorry, this omega is this one, okay? This is the omega. So this is the omega. So this omega square becomes then 4 pi square by t square. Therefore, that is the third law of Kepler's. Based on this only, see, we can calculate the mass of the sun. So 4 pi square by g ms into r cube. See, now time period of revolution is known, r cube is known, and now we can calculate ms. Why? Because g is also known. G is 6.67 into 10 to the power minus 11. So g is nothing but 6.67 into 10 to the power minus 11 Newton, whatever the unit you can figure it out. And what else? T is 365 into 86400. Why 86400? In seconds I have to convert. So this is second because all things are in SI unit, right? And last is the R. R I have already mentioned here. So you can calculate the mass of the sun from here. So mass of the sun will be, I have calculated it out, I think it comes out to be nearly 2 into 10 to the power 30 kgs. Please verify it. This is interesting to know. Fine. So this is the mass of the sun. And next thing is that what I thought is to tell something about the Earth's magnetic field. Although this is also a topic of research, still it is not known how the Earth generates its magnetic field, whether it is the mantle region which is generating magnetic field, because mantle is some molten fluids are there, and these fluids have charged particles which rotates with the Earth, and because of which this charged particle when rotates, a current flows and a magnetic field comes, and we generally denote it with this particular thing, that this is the Earth and there is a magnet, there is a bar magnet which is there. Actually this is not the correct thing, but still as a theoretical thing we can do this particular, in this way we can talk about this. Okay, and this is suppose the true north, true south, or the geographical north south. Now actually this is actually the south of the magnet, this is actually the north of the magnet. So this is how the thing goes. So from south to north, I think inside, so this is this will be the thing, north to south is the magnetic field lines. In this way the magnetic field is drawn. Actual thing is that there are two meridians, one is the geographical meridian and another is the magnetic meridian. So if I can draw, you can visualize this in this way. This is the geographical north and this is the magnetic south, maybe because whenever you take the magnetic compass, it points towards the north, but this magnetic compass also has a magnet. So if a magnet is pointing towards the north, that means some magnetic south of the Earth must be there, then only it is attracting towards that. So that's why it should be the, so this is the magnetic meridian, this plane is the magnetic meridian, right? And this is the geographic, what we generally see. Okay, now this angle is known as the angle of declination, delta, angle of declination. This is, I am giving the theory, nothing else. This is the angle of declination, this is an angle of inclination, although these things are not covered properly. I think in this course it is not well covered, but a slight introduction is required. So this is the angle of inclination or dip, magnetic dip, what we call. So this is magnetic dip. Okay, and this is the resultant vector, this is the horizontal and this is the vertical. So ultimately the resultant vector should be equal to the horizontal magnetic field plus the vertical magnetic field. This is some basic mathematical things about the Earth's magnetic field, but Earth's magnetic field does not look like this. I will try to draw it, and it is there also in the, I think the second or third lecture in the week 1. So suppose this is the Earth, the magnetic field is somewhat more complicated. So this is how it is made. Let me draw it properly and then I will explain. Just give me some minutes. Like this. Originating from the same point. Okay, and here also it is going like this, so it is going like this. Some complicated magnetic field lines is arising. So these things you can see that sun is in this side, so solar flares generally comes from the sun. Plasma, solar flares are nothing but plasma, ions, well, at a speed of some 450 km per second, So what, because of this high supersonic speed, supersonic greater than the speed of the sound, these solar flares comes and it creates a region of a shock wave. So whenever supersonic jets, you can read the concept of the shock wave. This is known as the bow shock region. So this is bow shock region, where is shock wave. So it provides actually a resistance. This is the outer part of the magnetosphere of the Earth. This results into shock region, which provides resistance to these solar flares. Okay, this provides resistance to the solar flares, but still some charged particles goes inside. Some charged particles may come, and what happens is that there is some magnetic field of the Earth. Now these charged particles, when it comes into a magnetic field, what happens? It starts a helical path, and this helical path will take these particular charged particles. Let me change the color. They take these charged particles towards these poles, these polar regions. And what happens in the polar regions? Some nitrogen, some oxygen, these atoms are there. Okay, these atoms are there. These atoms, they interact with, these charged particles interact with these nitrogen and oxygen atoms, and the electrons goes into the excited state, and when it falls, when after losing all the energy, when it falls, it releases some photons, h nu, some photon, and this sometimes looks as green based on the composition, whether it is nitrogen and oxygen. It looks like somewhat green, sometimes reddish. So these are known as the aurora phenomena. A brief introduction of aurora phenomena I have given here, and this is a complicated magnetic field, and this is a process which goes on inside the inside the magnetosphere. Well, that's all in this week 1 lecture, which I want to show you now. Okay, just a minute. Yeah. So these are for the week 1 lectures. Some important mathematical derivations and concepts which are very fundamental to know. I am coming to the week 2 lectures. I will slightly introduce the week 2 lecture also, because well, most of the questions in the assignments, I think it is from the from the vertical structure of the Earth, but I am planning to start with this some basic laws of thermodynamics kind of, so Charles' law and Boyle's law. But let me just discuss that particular thing, the vertical structure, maybe just a minute. So this is the thing, vertical structure of the atmosphere. So what happens is that it's a zigzag kind of a structure. Oops. It's a zigzag kind of a structure. So if I draw it properly, this is the height and this is the temperature. Okay, this is the temperature. This is maybe 0 degrees Celsius. This may be 20 degrees Celsius and some values, and this is maybe minus 90 degrees Celsius, like that way. Now this is your troposphere. I will explain each and everything, just wait. This is the troposphere, this is the stratosphere. Let me dissect it out. This is mesosphere, and after that is exosphere, or we call sometimes some portion is ionosphere, some portion is thermosphere. Okay, together it is called as the exosphere. It marches into the space. Fine. Generally these things occurs in 10 kilometers, 10 to 16 kilometers. It varies. This troposphere varies, and this is at a height of say 50 kilometers. The stratosphere ends. This at a height of 90 kilometers. Mesosphere ends, and this temperature is maybe minus 80 degrees Celsius, what I remember. Okay, so this is the troposphere. Let me do one by one. This is troposphere. So what happens in the troposphere? Temperature decreases with height, and since the temperature decreases with height, most of the weather phenomena, I would say that almost all the phenomena means what phenomena? Weather phenomena or atmospheric phenomena occurs in this particular zone, the lower portion, in the troposphere, right? And the temperature decreases linearly. It decreases first, okay. After that, on reaching the troposphere, what happens is that there is a pause. This pause is for the equilibrium between the stratospheric air and the tropospheric air. So why there is a pause? Because stratosphere is generally, okay, let me write the stratosphere first. Stratosphere, then is mesosphere. Okay, so in the stratosphere, sorry, in the stratosphere, this temperature generally increases with height. Okay, and then there is again a pause. I will explain each and everything, and now this decrement is much high. Okay, and it goes here. The minimum temperature achieved in the atmosphere is in this region, which is called the mesopause, and after that the temperature goes on. And sometimes in this ionosphere or thermosphere, I think in this lecture also they have mentioned that temperature goes up to 2000 Kelvin, similar to that of the corona in the sun. It goes about 1 million Kelvin, but below that the temperatures are less, quite less. But how it can be happening? Because there is very little amount of gas molecules which are present here. Now each molecule's temperature may be 2000 Kelvin or near that. So it is not felt properly. Its density is so low here. As we go up, the density is so low that your what you call as your temperature, although may be very high because the sun's radiations, shortwave radiations, it is maybe absorbing, because some oxygen atom may be there, it may absorbing, but it is not going to be felt properly. Now generally these temperatures are measured using satellite drag. So satellite, when it passes through those regions, some particles generally hit that particular satellite's wall, and there they measure, some sensors are there in the satellite, they measure the temperature of these particles, and with that we can find out that these regions have temperatures 2000 Kelvin, but it is only for certain particles, not entire layer, because entire layer only consists of very small amount of gases. Well, come back to last three layers, which are very important layers. Here all the weather phenomena occurs, and its height changes. Why its height changes? Because in some places where the temperature is very high in the surface, I have given it a mean temperature maybe some 15 or 20 degrees Celsius, but sometimes in the equatorial region, what happens is that, suppose this is the Earth, I will discuss the general circulation theory also in the next class, which is very interesting theory. You will understand there also. So this is the equator. In equator, what happens is that, and this is called the subtropical high. I am explaining it. Let me explain slightly. In details, I will explain in the next class. So this is 35 degrees south. This is 35 degrees north, and there is a low pressure belt here, some 60 degrees north, and this is 60 degrees south, and this is 0 degrees equator. Okay, this is the latitudinal way I am traveling. So winds generally move in this way. So winds generally move in this way near the equator, and the convergence takes place. The air converges in the equator, and since the air converges over the equator, where it will go? So this is the plane at the equator region. So air is coming from the north, air is coming from the south. It cannot go below because there is a surface here, so it has to move above. And because of this strong air motion created by high temperature zone over this region, a low pressure is created, and because of which the winds are coming, and because of which the tropospheric height or tropopause height is increasing. And as you go more towards the high latitude region, this tropospheric height generally decreases. So 16 kilometer mostly occurs in the equatorial region, where the temperature is very high, where convection is occurring. All these terms will be clear to you. It will be very easy. thing, but in the next class or the subsequent classes I will discuss about all these weather things very in a detailed manner, such that you will feel interest in this subject. Fine, let me focus on this particular what you call as this vertical structure of the atmosphere. So what is happening is that the temperature decreases with height, and there is a pause because stratospheric air, the stratospheric air which I was discussing, it is much more dry. Stratospheric air is dry, you remember this, this is dry and this is much more wet, moist. Why moist? Because moist air can come into this particular region, this particular region, because oceans are there in the surface, so from which the water vapor can come in here, and as a result some moist region, it's much more wetter as compared to wet is not a good word to use, I would say it's moist. So some dry air and moist air is there, so there is a kind of an equilibrium which is setting up here, and based on after that what is happening, the temperature is rising. Why the temperature is rising? Temperature is rising because in these regions, say from 16 kilometer to 35 kilometer, ozone layer is present. Ozone layer is continuously getting created, ozone is continuously getting created and destroyed. And both requires UV radiation. Both for creation of ozone requires UV radiation, and for destroying of ozone also it requires UV radiation. This ozone thing also I will discuss if I get some time. Today only I can discuss, maybe. It will be very interesting to discuss this particular thing, the ozone layer. Same UV radiation is creating the ozone, but this same UV radiation is also destroying the ozone. This particular region has ozone and this UV radiation. Now tell me one thing, this UV radiation is a shortwave radiation, right? Because it comes before the visible. If you see the electromagnetic spectrum, these are shortwave radiation. And since these are shortwave radiation, remember the Wien's displacement law, lambda max into T is constant. So if lambda max, the intensity of UV radiation is maximum in this lambda max, if it is very high, if it is very low, because it's a shortwave radiation, then temperature will go up in this layer. Actually this ozone is absorbing this UV radiation and resulting into high amount of energy, releasing into high amount of energy, and because of which the temperature is going up. As we come near to the stratosphere, again there is a temperature contrast. This is cooler as compared to this. So there is a pause here. So this pause is known as, let me change the color again. This pause is known as the tropopause. This pause is known as the stratopause. The above pause is the mesosphere and thermosphere. This is known as the mesopause. Easy to remember, isn't it? Because just the below layer, whatever is the name of that layer, that pause, tropopause. If we are talking about troposphere, remove this sphere, tropopause, stratopause, mesopause. Okay. Now here the temperature again starts decreasing because no such absorption is taking place over this region. Moreover, this mesosphere also have some nitrogen and oxygen. Okay, then why can't we survive in the mesosphere? This is because the density is too low. Density is too low, and not only that, temperature is it's also very cold. It's not for us to survive there. Nitrogen and oxygen may be present, but the amount of air we breathe, the mass of nitrogen and oxygen, or the particles of nitrogen and oxygen which we are breathing in, is not the same. It is very less as compared to what we are breathing in the surface. That's why we cannot survive here. So density is very low. Okay, so now the temperature reaches the minimum of minus 80 degrees, and in the mesopause, this is the minimum temperature in the observed in the atmosphere, and after that thermosphere, where ions may be present, and these ions generally absorb some radiation, and as a result of which the temperature goes up. This is the simple vertical structure of the atmosphere. You can do as many as questions in the assignments, very simple questions, so you can easily do it. based on the simple concept and also the concept which are covered in that NPTEL lectures. If you read it, you can, I think you can easily do it, this particular thing. Okay. Another thing I want to discuss here is, well, I will start with some basic laws. This one, yeah. So these are known to us. Charles' law, Boyle's law, these are all known to us. So fine. So Charles' law tells that pressure is directly proportional to temperature when V is constant. So what you get is P is proportional to temperature when V is constant. Great. Charles has given another law which tells that volume is directly proportional to temperature when P is constant. So Charles has actually given two laws. Okay. So Charles' first law and second law you can say. So P is proportional to T when V is constant. V is proportional to T when P is constant. So actually what happens is that P, V, T are state variables, thermodynamic state variables of the system. So if one of the twos are varying, or the two things out of three are varying, then one of the other thing must be constant. Then only these things will be satisfied. Okay, so these are the two laws. Second law is what? Boyle's law, which tells that P is inversely proportional to the volume when T is constant. See, another thing is constant. The third thing is constant. P and V are varying, T is constant. The third thing is that Avogadro's law. Avogadro's law tells that equal volumes of two gases contains equal number of moles. What is number of moles? Number of moles is defined as, so when you are doing the thermodynamics, actually this concept of moles, these things will occur, the specific heat capacity, these things will come, and I will discuss it in great details, no doubt about that. So it will be some given mass, given mass by molar mass. Okay, these are the number of moles. So if you take two gases, two different gases, maybe nitrogen and oxygen, this is nitrogen suppose and this is oxygen suppose. So nitrogen is about 28 grams per mole and this is oxygen is about 32 grams per mole. So molar mass is known to us. Now if we take the same volume of gases, maybe different gases, but it will contain equal number of moles. So number of moles is denoted by N, is given by mass by molar mass. So there is a particular ratio of the masses we can get based on this molar mass difference. So what is happening is that number of moles will be same because the volume is same. So M1 by capital M1 should be equal to M2 by capital M2. So M1, M2 is known. So M1 by M2, this small m1 by small m2 is calculated using this ratio of the molar masses. So ultimately what does it tries to say is that volume is proportional to the number of moles. Okay. Now combine all these things. P is proportional to T, V is proportional to T, P is inversely proportional to V, and V is proportional to N. What we get is what we call as the equation of state, the ideal gas law. This is the ideal gas law. So what we get is PV is equal to NR star into T. Now what is R star? Known to us, it is universal gas constant. This is universal gas constant. R star, whose value is constant, 8.314 joules per Kelvin per mole. Remember, this is joules per Kelvin per mole. After this, maybe in this class or in the next class, I will create a concept of a specific gas constant. I am writing here, I am not discussing it right now, specific gas constant. Now, let me tell you very clearly, this specific term, this specific term means per unit mass. So, we can say in thermodynamics, we will say in thermodynamics in the maybe in next couple of lectures that specific volume. Specific volume means then what? Volume per unit mass. This is the specific volume. We generally talks about that specific heat capacity, Cp, Cv. these all are per unit mass. Similarly, the specific gas constant, which is now in per unit mole, that will be now in per unit kg. We will see how it is done. Now slowly and gradually we are going towards the thermodynamical things. Okay. Now, okay, this is the composition of the atmospheric air. Before that, I want to ask any question, whatever I have covered in that. If there is any question, then we can discuss that. Or should I go on? Can anyone respond? Oh, I'm sorry. Just a minute. Can you see my screen? Yeah. Yeah, tell me. Someone is asking about double mesopause. Okay, someone has asked here that whether carbon dioxide concentration reached from 0.03 to 0.04%. Well, yes, it has reached to 0.04% and it is growing about 415 parts per million, and it is growing, still growing. So anthropogenic activities should be stopped immediately. That is what all people are trying, and otherwise this global temperature will rise, and it may be possible that we talk about Venus. Venus is Earth's twin planet, and see what is the condition of Venus. It is 96% carbon dioxide today in the Venus, and because of which the greenhouse gas effect is so high that its temperature has gone up to 700 Kelvin, the surface temperature. So it's true that that your this carbon dioxide is going up, and we have to control it by different mechanism. We have to control it. Although electric cars have come, different things are coming. So we people also have to look into this particular matter in great details, maybe in the future, so that the future is safe for us. Okay. Fine. Okay. Any other question? You can write in the chat box. Better, I can see and answer it. Okay. So before starting this composition of atmospheric air, let me slowly discuss that ozone kind of thing. The ozone is left. Okay, let me get a blank slide maybe. Just a minute. Patience and wait. Just a minute. I will add a blank slide. So let me see the reactions. Wait a minute. Yeah. So ozone, what happens is that there is a region of UV in between 0.176 micrometer to say some 0.25 or 20 micrometer. This is a region of UV, and another UV region is, suppose this is one UV1, another UV2 region is in between 0.20 to 0.40. Because after 0.40 micrometer, what happens is that visible region comes. So this shorter radiation this UV1, when ozone is interacts with UV1, or this UV1 means the photon of UV1, O3 plus H nu of this UV1. What happens is that this O2, it dissociates into O2 and nascent oxygen, free atom oxygen. Okay, now what happens is this O3, again another ozone molecule, O3 again plus this nascent oxygen, it cannot react, but with some other molecule, if another molecule exists, then it reacts to form 2O2 plus M. This is just to take the extra amount of energy such that the energy is conserved. For energy conservation only this extra mass or extra molecule is required. Okay, so this is the reaction of ozone, this is the reaction of, I think I had made some mistake, sorry. This is O2, oxygen to, this becomes nascent oxygen, okay, and then O2 plus O gives ozone, O3 plus M. This is the reaction. So this is the ozone creation. I was writing about the ozone destruction here. The ozone creation. So how ozone is created? I will write in the next class the actual reaction. So O2 plus H nu, this is a rough thing I am doing. The O2 plus H nu gives the nascent oxygen, and O2 plus this nascent oxygen cannot conserve the reaction. That's why another atom, if we get, then O2 plus nascent oxygen plus that another atom will take up the extra energy and form ozone plus that molecule. Okay, and ozone destruction is what I have written earlier. So ozone destruction reaction will be O3. Now H nu will be of this UV2. This UV2 will be this H nu, and that will give O2 plus this nascent oxygen, and again another ozone molecule plus this nascent oxygen will give you 2O2. So ozone now is converted into oxygen molecule. This is ozone destruction. Okay, so this is ozone creation, this is ozone destruction. So this is what I was talking about. The ozone, you people have heard about the ozone layer, which there is a hole in the ozone layer in the Antarctic region. Actually what happens is that stratospheric air also has a circulation. So what happens is that this is suppose surface, and this is the troposphere ends, this is the stratosphere. So there is a weak circulation which occurs in the what you call as in the stratosphere as well. So these stratospheric circulation will take this ozone towards this ozone, or these molecules which are present in the stratosphere, towards this Antarctic polar region, because it is generally from equator to poleward this transport takes place, which is also known as the Brewer-Dobson circulation. I'm not writing it because it's somewhat not related. So this here what happens is that those CFCs, the chlorofluorocarbons, CFCs, I will give the detailed reaction how these ozone is destroyed using the CFCs. I will give everything. So this CFCs goes towards this Antarctic region and harms this ozone. It destroys this ozone, and that's why there is an ozone hole which is being created. For a long time after that Montreal Protocol came, and then that refrigerant was changed, because most of the CFCs chlorofluorocarbons were used in the refrigerants only. So that is a very harmful gas. That is a very harmful gas. Not harmful in the troposphere, maybe for us may not be harmful, the CFCs. That's why it is used as a refrigerant. But you can understand it is harming where. So it is going into the upper atmosphere. Somewhere it is getting, it is providing some destruction to us. Because in this Antarctic region, what happens is these UV radiations are coming, penetrating. It is harmful for the animals there which are present there. So these are the things. Not only that ozone hole is coming over this region, somewhere here also some ozone destruction can also harm us, because the UV radiation it is absorbing. So that is what I was trying to discuss. And after that, so this is the composition of the atmospheric air. uh, I will not go into much details after this, because after this I have to uh, tell you about the dry air and the mass of the vapor. This will be much more interesting. Maybe in the next class we can start this. And before that, any other questions, or we can discuss from this. So you can say that, yeah. Yes, okay. If you know the term double mesopause, which is the coldest temperature on the earth, will you please explain? No, see, double mesopause I have not heard, but mesopause is that the actual temperature where the temperature is minimum, say about minus 80 degrees Celsius, which I have shown you. What I know is that I have not heard the term double mesopause, but it is mesopause where you will find the minimum temperature. And mesopause, why? Because it is an equilibrium region between the high temperature thermosphere and low temperature mesosphere. That is what I know. Double mesopause, I will search and I will let you know. I am not very sure about that double mesopause thing. And any book to follow? Well, there are many books. You can read Wallace and Hobbes. That's a very good book. Well, I'll write it here. Wallace and Hobbes. And any other book which they have recommended, maybe the NPTEL has recommended, that book also you can follow. But Wallace and Hobbes is a very good book to understand the basics very clearly. That's a very good book to start with the atmospheric physics and science. That is very good. So you can start reading it slowly and gradually. You can read it. That's a very good book. If you are feeling interest, then you should go ahead and read those books. And a slight discussion about the greenhouse gases in this particular thing. You know that greenhouse gases are those gases which oh, of course, there is another thing which I have forgot to mention. So greenhouse gases like carbon dioxide, why is it harmful? Because CO2 is a greenhouse gas, we know. CO2 is a greenhouse gas. Since someone has raised the question of greenhouse gases or global warming, whether its concentration has increases or not. So CO2 is a greenhouse gas. So what effect is it giving? See, we have calculated that lambda max for the earth with temperature is equal to 288 Kelvin. The lambda max lies in the range of 10 micrometer. And what is the 10 micrometer? It is the infrared. These greenhouse gases has the property. To absorb infrared radiation, absorb IR radiation. And since it absorbs IR radiation, it also emits. Okay, it absorbs IR radiation, it emits also. And that's why what happens is that, suppose this is the CO2 layer and this is the surface of the earth. This is surface and this is CO2 layer. What is happening is that earth is emitting because it has some temperature 288 Kelvin. Now it is getting absorbed and it is re-emitting back. So what is happening? All the heats are trapped in this region, and this is why global warming takes place. This is happening for a long time, and that's why this global warming phenomena is taking place. So CO2, the most largest gas is water vapor. You know, the most largest greenhouse gas which is present is water vapor. But water vapor is not very harmful. Why? You know, because water, this H2O exists in three forms. It exists in both three forms: solid, liquid, as well as vapor. So vapor is dangerous, but solid and liquid is not dangerous. The ocean water and this, so conversion can take place in water vapor, but in carbon dioxide it cannot take place. I will show you in the next class. It's a very good point that carbon dioxide someone has written. I suddenly remembered it. So why carbon dioxide cannot be what you call as converted into these states, solid or liquid states? Why it cannot be converted, at least in the liquid states? If it can be converted into liquid state, then it will not be harmful. But it is not be possible, because for that there is something I will tell you in the next class. I remember it. Okay, fine. And Other greenhouse gases like this water vapor is a greenhouse gas, CO2 is a greenhouse gas, then this one, ozone. Ozone is also a greenhouse gas. Then N2O, nitrous oxide, is a greenhouse gas. Then, okay, I am writing CO2 here so that I will write it here. So CO2 is a greenhouse gas. Then what more? CH4, methane. Methane is a greenhouse gas. So these are all greenhouse gases. Just for writing it down. So these are the GHGs. And GHGs has a property to absorb the infrared radiation and it re-emits back, and as a result of which the Earth's temperature goes up. So with this, I think I should end the session. Because in the next class I will start from here, the composition of the atmospheric air, and we will study about the mass of the dry and the mass of the vapor, dry air and vapor. Actually, atmospheric air has only two things, either dry air or the vapor, and this dry air and vapor together constitutes the moist air, and I will also tell you about this moist air thermodynamics and things. NO2 is greenhouse gas or not? You search it. I think this is a question from the assignment. You search it. How can ozone play a role in global warming? No, ozone does not play a much role in global warming, but it's a greenhouse gas. It of course gives some temperature in the earth, but the maximum is of carbon dioxide, because ozone, as I have already told you, that ozone is destroying as well as it is being created. So something which is being destroyed and created, it is not going to play a much big role. Although CH4 is a very small amount, it is present. All these concentrations are very less. So ozone's concentration is much less, I think, than this carbon dioxide. So carbon dioxide is coming here, isn't it? So it will not matter much. Ozone's role playing in global warming will not be very high. But I think the only gas which is mattering here is carbon dioxide, nothing else. That is the big thing, and several discussions were going on in this way. Anything else? I will prepare these slides, whatever I have written, and I will share it to the NPTEL sheets they have provided. I will also try this recording. I will also put into the YouTube. The link will be given. It will be shared with you. Within 1-2 days, it will be shared with you, so you can use it. So this session is useful or not? Have you felt interested or not? Just can you tell me, or some other things I should do? Can anyone just write or? Great. Fine. I am just going slightly deeper. I will go more deeper because this subject is very good. It is an interesting subject. Even if you go deeper, you will feel interesting. So that's nice. Okay. Thank you. Anything to change? Means I am more focusing not only on theory, more on the concepts and some numerical based aspects, some derivations maybe, but very little bit. Not much numerical can be covered from these things. That's why I have put this way. Okay, so I am then stopping this. Just wait.